All right, so in today's lab, we are going to experimentally determine the equilibrium constant. And we're going to do that using the ferrothiocyanate ion. So we're going to start with a solution of iron nitrate and potassium thiocyanate. The nitrate and the potassium are spectators, that's why they don't show up. And these two ions are going to react to form a complex ion that we call ferrothiocyanate. It's got an orange color, so it's very obvious, it's very apparent that it has formed. Whereas these two are going to appear relatively clear. So the equilibrium constant will be calculated by taking the equilibrium concentration of the products over the equilibrium concentration of the reactants. Now, because this is a colored solution, we're going to be using a colorimeter, and the colorimeter measures absorbance. And for the purposes of this lab, the absorbance is proportional to the concentration of the ferrothiocyanate. Okay, so in order for this to work, we need to first establish a standard curve. So that's what part one is all about, is establishing the standard curve. So here we have iron in 0.2 molar and thiocyanate in 0.002 molar. Notice that the iron is 100 times the concentration of the thiocyanate. And the reason for that is we want to ensure that the thiocyanate is going to be the limiting reactant. By far, it's going to be the limiting reactant. Like we said, the ratio is 100 times of iron compared to thiocyanate. And the reason why we're doing that is that's going to ensure that all of the thiocyanate reacts. Whenever there's a huge disproportionality between the two reactants, we're ensuring that the one in smaller concentration is completely consumed. So the reason why we want to make sure that's completely consumed is so that we can then assume that whatever concentration of the complex ion product forms is based from using up all of the limiting reactant ion, the SCN. And because we are measuring and we know the known molarities, if this is known, then this can be known as well. So that is why we need to have such a huge difference in concentrations. All right, so once we test those solutions, so by the way, these proportions here are all in milliliters. So tube one, for example, will have 5 milliliters of iron and no thiocyanate, and it's gonna have water as well to make a total of 10. So 5 milliliters of water, which I didn't write. All right, so once we get a plot, we're gonna plot our absorbance versus our molarity of FeSCN. Now remember, this is known because we are making the assumption that the FeSCN is equal to the SCN concentration. So we'll plot a curve, we'll get a regression. That regression is going to be important. All right, part two, we're going to have an unknown solution of SCN, meaning we don't know what the concentration is, but we're just going to mix a known quantity of SCN with a known quantity of iron, and we're going to produce a product, and we're going to test the absorbance, and we're going to use the regression to determine the concentration of SCN. In part three, we're actually going to prepare and test equilibrium systems, but this time the concentrations that we're using of the iron and the SCN are the same initially. So 0.002 molar, 0.002 molar. And we are varying the concentrations, and by varying the concentrations, we will get different absorbances. Now, the total volume is controlled at 10 milliliters, which is why for water, the corresponding amount of water represents whatever is needed to make a total volume of 10. Again, once we have the absorbances will enable us to find the concentration of FeSCN. To solve for the equilibrium constant, in a typical ice table, the proportions of the reactants are known, so this initial concentration of iron can be calculated. The initial concentration of thiocyanate can be calculated. and we do not have any product from the onset. Now, after testing, the absorbances is caused by the product, which is colored, and so we can use a regression and we can figure out the concentration of the product. Now, because the product started at 0 and is going to have some value at equilibrium, then the rate of change can be determined. If the rate of change is determined for the product, then we know the rate of change for the reactants as well. So we can calculate the equilibrium concentrations of the reactants by applying the rate of change from the initial concentrations. And that would give us all 3 equilibrium concentrations so that we can solve for the equilibrium constant. Now, you're going to run several trials, so your equilibrium constant will be an average of all the trials that produced an equilibrium constant, all the trials from part 3, that is. In part 4, we are going to run the controlled sample reaction, and we're going to test this in a hot water bath and a cold water bath. That is to say, the reactants will be sitting in a warm bath and a cold bath before mixing. We'll take the temperature, we'll mix them, we'll test the absorbance, and then we will determine the value for Kc, and so we can answer the question, is this reaction endo or exothermic? Meaning, how is it influenced by the addition or removal of heat? Does it shift to the left? Does it shift to the right? That's what's going to help us to determine whether the reaction has a negative delta H or the positive delta H. All right, so we need to set up our lab quest. So for starters, I'm going to take our colorimeter and plug it into channel 1. And then I'm going to change the mode. And this is going to be events with entry. And the first column, it's going to be molarity. Molarity. And units. M. Okay. So now let's start prepping the solutions. Okay, so we are going to prepare a blank so that we can calibrate the colorimeter. So I'm going to take my cuvettes, just add some deionized water, and I need to make sure that the wavelength setting is at 470 because the solution we're anticipating is to be red. And now I'm going to hit the calibrate button. And now we're calibrated. All right, so we've just made solution 1. This is beaker 1 on the front of your data table. And I went ahead and poured it in here. I rinsed this a couple times. And so we're going to test its absorbance. Now, this does not have any thiocyanate in it. And the absorbance is reading 0, which makes sense because there was no colored product formed. So we're going to keep this, and the concentration of the FeSCN is 0. So that's going to be our first point. And we're going to go on and make solution 2 and test that as well. Okay, so we've just made solution 2, and I'm going to rinse the cuvette a couple times. All right, so absorbance for beaker 2 0.270. Okay, and the molarity for this, using the dilution formula, was 0.00008, or in other words, 8 times 10 to the negative fifth. And we are going to prep solution 3. All right, so we just prepped solution 3. Gonna rinse the cuvette. Okay, so it looks like 0.03 or 0.382. Let's keep that. Concentration is 1.2 times 10 to the minus 4, or in other words, 0.00012. All right, on to solution 4. All right, so here comes solution 4. We're gonna rinse our cuvettes. All right, molarity, 1.6 times 10 to the minus 4. Okay. All right, and solution 5. All right, so it's going to be 0.0002. All right, and so those are our values. Okay, so in part 2, we are going to make an unknown solution from this SCN solution of unknown concentration. We're going to take 5 milliliters of it, and we're going to combine it with 5 milliliters of the 0.2 molar iron, and we're going to make 100 milliliters of solution. We're going to test it and record its absorbance, and hopefully be able to determine what the concentration was using the regression. All right, so now we've got the unknown made. We're going to go ahead and rinse and fill our cuvette. Okay, so our absorbance is 0.491. Okay, for part 3, we're going to be using 0.002 molar iron solution, the same concentration as the thiocyanate, and we're going to establish a true equilibrium system here with varying concentrations of thiocyanate. And we're going to mix these in these test tubes, and we're going to test them like before. All right, so for part 3, tube 1, we're going to start testing. So our first tube did not have any thiocyanate, and which is why it doesn't have any color. And we're not going to plot this, we're just going to record absorbances this time. So as expected, we have 0 absorbance for tube 1. Okay, so this is tube 2. We did add thiocyanate, and hence there is some color to it. And we'll go ahead and record 0.162 for the absorbance. So this is tube 3. We'll go ahead and call it 0.235. 0.233. This is from tube 4. We'll call this 0.305. All right, and this is our last tube, tube 5. We'll finish here, 0.377. Okay, so this is part 4, and I've been letting these test tubes sit here in these different water baths now for about 10 minutes. One of them is at about 35 degrees Celsius, and the other one is about 3 degrees Celsius. So in one test tube, I have already pre-mixed the water and the iron solution. So all I have left to do is to add the thiocyanate into the mix, and then I can go ahead and test the solution. So let's go ahead and do that. So we're gonna need 3 milliliters of thiocyanate to make up a total solution of 10 milliliters. Okay, and this is the warm bath. This is the 35 degrees. Go ahead and rinse the cuvette. All right, so the absorbance at 35 degrees, 0.211. Now, the proportions of solutions for part 4 were 3 milliliters of the iron, 3 milliliters of the thiocyanate, 4 milliliters of water. And this was the same concentrations that we used in part 3, so 0.002 molar. All right, so I'm gonna test the cold ice, the ice bath. This is about 4 degrees now. So I'm gonna measure out my thiocyanates. Add it to the water and iron mix. So rinse a couple times. All right, so 4 degrees. .277.